What's up, Simpsonites? Let's keep going here. All right, periodic trends. So we talked about 4 of them. Okay, so let's start right here. Electronegativity. Electronegativity. Okay, now this is the ability of an atom to attract outside electrons. Okay? So I'll try and shorthand that. Ability of an atom to attract electrons. Okay, and specifically when it's bonded to something else. So we've talked about this a lot recently with water, where you have the oxygen bonded to 2 hydrogens, and the greater electronegativity of the oxygen allows it to attract the electrons that are being shared toward itself. Okay, so electronegativity is the ability of an atom to attract electrons to itself. Ionization energy. The energy required to remove an electron from an atom. The energy required to remove an electron from an atom. So this is kidnapping kids. Okay, this is why we start talking about kidnapping kids all the time, because we're talking about ionization energy, how hard it is to take away an electron, to take away a kid. Okay, ionic radius. You should have a better understanding now of what an ion is. So the radius of an ion of an element. So when an element gains or loses electrons, what's the radius of that ion? And lastly, atomic radius, which we specifically defined as the distance from the nucleus to the outermost electrons when an atom is bonded to another of the same atom. And that was just because if you have 2 atoms bonded together, or I guess more specifically, that's not a very central nucleus. It's the distance, half the distance between these 2 nuclei, because we're much better able to see where a nucleus is rather than where the electrons are. So if we have 2 of the same atom bonded together, we can assume that half of this distance is where their valence electrons are, therefore the size of a single atom. But atomic radius is basically just the size of an atom from nucleus to valence electrons. Okay, so those are the definitions. Now before I go into the specific trends for each one, let's talk about what causes these trends. So if we're looking at the periodic table, okay, and the first direction to look in is, make this bigger for this, from left to right across the periodic table, okay? Left to right. So what's happening as we go left to right across the periodic table? Well, like I just said a minute ago, or in the last video I should say, as you go left to right, each element from left to right increases by 1. The atomic number increases by 1. The number of protons in the nucleus increases by 1. Every proton has a positive charge. So every time you go to the next element to the right, you're adding another positive charge in that nucleus. And that increasing positive charge in the nucleus is going to have an effect on the valence electrons. Okay, the stronger the nucleus is, so if this is your nucleus of an atom and you have your energy levels, say we're in the 3rd energy level, the more positive and stronger this nucleus becomes, the more it's going to pull these outer electrons toward itself. The more strongly the nucleus is going to attract electrons, because the positive nucleus attracts the negative electrons. Okay, so as we're going across the periodic table from left to right, we have stronger nuclei attracting electrons more strongly. So that means if we're talking about what is increasing as we go across, it's going to be increasing ionization energy, because those nuclei are holding the electrons more strongly. It's harder to take them away because they're pulling them in tighter and tighter. It's also going to be increasing electronegativity. Okay, because those stronger nuclei are attracting electrons more strongly. So they're going to pull in outside electrons more strongly. That's why we say oxygen pulls the electrons more than hydrogen, because it has higher electronegativity. It has a stronger positive nucleus. Okay, so of our 4 trends, those 2 are increasing. And if in your notes or on the study guide you drew individual lines, that's fantastic. You don't have to do it this way. I'm just trying to show you how they pair up, kind of. Okay, so that's what's increasing. Now, let's swap colors and let's talk about what's decreasing. If we drew this line as decreasing, the atomic radius, it's a nice color, the atomic radius is going to be decreasing, because if the radius is the distance from this nucleus out to these valence electrons and they're getting pulled in tighter as you go across, that radius is going to be decreasing. The size is going to be getting smaller, okay, because the protons, you're getting more protons pulling those electrons closer. So the size of the atom from nucleus to valence electrons will be getting smaller. Now, in general, the ionic radius also decreases. But recall, so everything from this over is going to be losing electrons to form an ion. All of these are going to be getting rid of their electrons to form ions. Everything this direction is going to be gaining electrons. So it decreases here, from here to here. Then it goes up again because you're gaining electrons. So instead of an atom, so the ionic radius, okay, if this is sodium, okay, and it wants to just get rid of its third energy level, it's getting much smaller. However, if we stay in the third period and this is nitrogen, so it has 1, 2, 3, 4, 5 valence electrons, and it gains more. It's keeping this energy level and staying bigger. However, as you go across, you're still getting more protons and you're pulling them in tighter. So that's why we had this double arrow here, if you remember, for ionic radius, where it's decreasing here, but then it jumps up again and then decreases for that as well. So up until this group right here, you're losing electrons, so the ion's getting much smaller because you're losing an entire energy level. Then from here on, it's keeping that energy level, but they're still getting pulled tighter, just like atomic radius does. Okay, so those are the trends across. Atomic radius, ionic radius decrease across because the electrons are getting pulled tighter. Electronegativity and ionization energy increase across because the additional protons are pulling the electrons more tightly. Tighter, more tightly, what have you. Okay, so let's look at what happens as you go from top to bottom on the periodic table. Okay, so from top to bottom, every time we go down a period, every time we go from hydrogen to lithium, lithium to sodium, sodium to potassium, every time we do that, we're adding another circle. So first period, first energy level, second period, second energy level, third period, third energy level, fourth period, fourth energy level, so on and so on. So we're adding energy levels. And that's doing 2 things. For one, it's making the energy level, the outermost energy level, further from the nucleus because you're adding another one. And for another, it's creating all these electrons in between the nucleus and the outermost electrons. Okay? Because every time you go down, you're adding another full energy level from the period before. So when you jump, for sodium is 3s1 and potassium is 4s1. But when you go from 3s1 to 4s1, you are saying that you had 3s2 and 3p6. You had 8 electrons in between. Okay, so that's what's happening. You're adding more energy levels, and you're adding more you're adding more shielding electrons in between the nucleus and the outermost. So let's talk about our trends. Electronegativity. As you go down, let's talk about this the same way I did last time. So let's say that this line is representing decreasing this time. So as you go down, the electronegativity is decreasing because electronegativity is the ability of the nucleus to attract outside atoms. So if you have your nucleus here and you have 1 energy level, it's going to be pretty easy to attract to attract other atoms because there's just 2 electrons between it. If you had another energy level with 8 electrons, I don't know if that's 8, but another full energy level, it's going to be a little bit more difficult because you have more electrons in between the nucleus and this electron that might be passing by. Okay, and then you add another energy level, it's going to be even harder. And you add another energy level, it's going to be even harder. So all of these shielding electrons, all these electrons between the nucleus and an outside electron are going to decrease the electronegativity as you go down and add more and more energy levels. Okay, also ionization energy. Okay, is going to be decreasing. So because it's going to be easier to remove these electrons. Ionization energy is how difficult the energy required to remove one valence electron. So with this, you have all these electrons in these 2 energy levels interfering with the nucleus's effect on that. And then the more energy levels you add, the more shielding electrons you add, the easier it is to take away the valence electrons because you have all these interfering electrons. So this is where we're talking about kidnapping kids. And if you're at Disney World and the mom is standing there and she has 2 kids on leashes, okay, you're not going to get one of those kids. But then if you have this mom over here, her hair's kind of crazy because she has so many kids, and she's got kid, 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 kid. All right, and you spot the outlier just right here. That's a quick grab and go. Okay? This kid is going to be easy to steal from this mom. These kids aren't going to be easy. So this is like helium, just 1 energy level, 2 electrons, 2 kids. And then this is going to be, I don't know, someone with a bunch of, then you can take the outermost kid really easily. Okay? So that's how we bring this into something relatable. So ionization energy is decreasing as you go across because decreasing ionization energy means it's getting easier to take away the outermost electrons. All right, so those trends decrease as you go down the periodic table. Oh no, I don't want to erase that. How do I cancel my erasing? I can't. Okay. Redraw. Okay. So now let's talk about what would be increasing. Well, the radii, so atomic radius and ionic radius. Because as you go down, if every time you go down you're adding another energy level, obviously you're increasing the radius because every time you add an energy level, this radius is getting longer and longer and longer. All right, so as you go down and you add new additional energy levels every time you jump to a new period, you are increasing the both radii. Okay, so there are your trends. That's it for ionic trends. And I could stop this video and continue after, but I'd rather let's just wrap it up. What do you say, kids? Okay. So we just talked about this. It's protons in the nucleus. It's shielding electrons as you go down. Okay, stuff like that. Every element in a period has valence electrons in the same energy level. Okay, so if you're in the second period, first period, 1s1, 1s2, second period, okay, 2s1, 2s2, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. This is a full second energy level, but as I was doing that, we were just going from lithium to beryllium, to boron, to carbon, to nitrogen. Okay, we're going across like this within the same period, but we're adding electrons to the same energy level. Okay, so the valence electrons are in the same energy level for any atom in any given period. Every element in a group has the same number of valence electrons. So they're going to be in different energy levels, but it's going to be the same. Okay, and for the second group, it would be 2s2, 3s2, 4s2, 5s2, 6s2, so on and so on. Okay, 1s1. Energy level. Suborbital. different shapes. Remember, S is a sphere, P is like this, and you can have the like this, and then you can have the third one like this, stuff like that, if you forgot that. So that's why we can have only 2 here, and then we can have 1, 2, 3, 4, 5, 6 in the P, and then D starts getting weird. And the exponent is the number of electrons. Okay, so S holds 1. S holds 2. P holds 6, D holds 10, and F holds 14. Okay, and it's because of the different shapes. You can go back and reference that slide if you want to, where we had all the different shapes out there, and we had, like, S always has 1 line that can have 2, and P has 3 lines that we filled in like this, and all that stuff. Valence electrons are the outermost electrons that interact with other atoms, determine the properties of the element. Electron configurations. All right, let me just do a couple of these to make sure you know what you're doing. And if you are getting them all wrong, you can still do the rest and Google the answer. So for the first one, let's talk about neon. So right here is neon. So first thing we do is target acquired. So we got to start here, just like a book, start at the top left, and we got to go across and down until we get where we're going. So we start at hydrogen, which is 1s1. Then we go across, and helium is 1s2. So that's going to be full, 1s2. First energy level, s suborbital, 2 valence electrons. Then we go to the second energy level, the s suborbital, lithium, beryllium, 2s2. We go across to here, which is going to be the p suborbital, so still the second energy level, p suborbital, 2p1, 2p2, 2p3, 2p4, 2p5, and 2p6. So this has, in the second energy level, it has 2 plus 6, 8 valence electrons. 8 valence electrons, which is a full octet. That's why it's a noble gas. Okay, next one. Copper. So part of this is being familiar enough with the periodic table that you can at least find the general area of where you're going. So this one, we're going here. Copper. Okay, so again, we start like a book, top left. So hydrogen, helium. 1s2. Go down to the second energy level. 2s2 is going to be full. 2p6 is going to be full. Then we go down to 3s2 is full. The 3p is full, so 3p6. Then we go down to potassium. 4s will be full. So now we're here. Okay, this is where we ended. So now we're going to the d orbital. And the key thing to remember is that the d orbital is 1 period behind whatever period it's in. So this is the 4th period, but this is 3d. Okay, so the first period is just s. Second period you add, or first energy level is just s. Second energy level you add p. Third energy level you add d. So this is the 3rd energy level still. It's the d block of the 3rd energy level, but it's in the 4th period. So 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9. 3d9. Now notice that the outermost electrons are still in the 4th energy level. It's in the 4th period, and its outermost electrons are still in the 4th energy level, but this element itself is in the 3d block. Okay, so where I said everything in the period has valence electrons in the same energy level, that is true for this as well, because it's in the 4th period. It may be 3d, but its valence electrons are still in 4s. So there's a little side note. Okay, so that's how you do electron configurations. Hopefully most of you remember that. Again, these 3, if you notice that you were doing it wrong with these 2, then do these 3 again yourself and check it online. All right, thank you guys. Another video will be